Now let's look into the third question, which says you have to prove 1 square plus 2 square plus 3 square plus 4 square plus n square is equal to 1 upon 6 into n plus 1 into 2n plus 1 using the principle of mathematical induction. We have to use principle of mathematical induction. Again, it is Pn. It is very useful otherwise also. You will be able to learn formulas also, because this is the sum of the squares of natural numbers. Sum of the squares of the natural number. The first question we did was sum of the first n natural numbers. 1 plus 2 plus 3 plus 4 is equal to n into n plus 1 upon 2. Second question we did was sum of the even positive numbers. 2 plus 4 plus 6 plus 8 till 2n was equal to n into n plus 1. Now we are talking about sum of the squares of the first natural number. 1 square plus 2 square plus 3 square plus 4 square. So this is very important for you. 1 upon 6 into n plus 1 to n plus 1. You should be able to remember these formulas also, because they will be used later on in mathematics in your class 12th as well as somewhere in class 11th, when we will be doing probably series. So 1 square plus 2 square plus 3 square plus 4 square plus n square is equal to 1 upon 6 into n plus 1 into 2n plus 1. So what we are going to do is, we are going to again do the same process what we have been doing in the earlier two questions. That first I am going to prove the statement to be true for n is equal to 1. Basic step. This is known as basic. You don't have to write every time. You don't have to write. It is basic step. I am writing as a teacher so that you remember it. What is the basic step? So that you remember in your mind what are the three steps you have to do. Basic step, assumption step, induction step. Basic step is that I am going to say n is equal to 1. So left hand side P1 will be equal to 1 square, that is 1. Right hand side, let me see right hand side what is the value of P1. If I put n is equal to 1, so it will be 1 upon 6 into 1 into 2 plus 3. 1 plus 1 is 2, 2 into 1 is 2, 2 plus 1 is 3. So 1 into 2 into 3. So 2 3s are 6 will cancel, you will get 1. So left hand side is equal to right hand side is equal to 1. So it is true. It is true for n is equal to 1. The given statement is true for n is equal to 1. Now let us assume that it is true for some value n is equal to k. Assumption step. Assumption. And what is the assumption? Let it be true. Let Pn be true for n is equal to k. Let's assume it is true for n is equal to k. That means we will replace n by k. It will become 1 square plus 2 square plus 3 square plus so on plus k square, and n will be replaced by k 1 upon 6 into k plus 1 2k plus 1. This step is important again because I am going to use this in the next step. I am going to use this value in the next step. Let us prove Pn is true for n is equal to k plus 1. So we will place n by k plus 1 now. So pk plus 1 will become what? It will become 1 square plus 2 square plus 3 square plus k square plus k plus 1 whole square. So this 1 square plus 2 square plus 3 square till k square is equal to what? 1 upon 6 k into k plus 1 to k plus 1. And we have added k plus 1 whole square. We have added k plus 1 whole square. Take the LCM. 6 will be the LCM. So k into k plus 1 into k 2k plus 1. 6 is LCM. I am doing it at the beginning, but you can do it yourself. 6. I can take out 1 upon 6 common because 6 is LCM. It is dividing the complete thing. Out of this you can take out k plus 1 common. You can take out k plus 1 common. What will be left inside? K into 2k plus 1, which is 2k square plus k. K will multiply 2k, will give you 2k square. K into 1 will multiply, will give you k. Plus k plus 1 has come out. 1k plus 1 has come out. Only k plus 1 remains. So 6k plus 6. It will become 1 upon 6 k plus 1. Let us see what does it become. 2k square plus 7k plus 6. Now this is a trinomial. Let us factorize it. 2 6 are 12, 4 3 are 12. 2 6 are 12, 4 3 are 12. What I'll do is 1 upon 6 k plus 1, then 2k square plus 4k plus 3k plus 6. 1 upon 6 k plus 1. You can take common here 2k. If you take 2k common, it will be left k plus 2. You will take 3 common and it will be left k plus 2. So final, what will be left? 1 upon 6 k plus 1, k plus 2 and 2k plus 3. Now let us check whether this satisfies the first statement. Now let us replace n by k plus 1. Let me put k plus 1 here. So what you get? 1 upon 6 k plus 1. You will get k plus 1, k plus 1. It will become k plus 2. If in place of n I have put k plus 1, 2k plus 2 plus 1. It will become 2k plus 3. And what is here? 1 upon 6, k plus 1, k plus 2, 2k plus 3. So it is true for n is equal to 1, n is equal to k, and n is equal to k plus 1. So it is true. So Pn is true for n is equal to 1, n is equal to k, and n is equal to k plus 1. So Pn is true. Pn is true for all given n, whatever the values of n is. Natural numbers, n are given as natural numbers. So it is true for all n. Based on the principle of mathematical induction. We have done 3 questions. First was sum of n natural numbers, n into 1 plus 2 plus 3 plus 4. The second was I think the sum of 2 plus 4 plus 6 even numbers. The third was 1 square plus 2 square plus 3 square. Sum of squares of natural numbers. Now it is sum of squares of all numbers. Odd positive number. 1 square plus 2 square plus 5 square plus 3 plus 1. We have to prove this mathematical statement to be true using the principle of mathematical induction. Again, we are going to follow the same process. The process is that I'm going to prove that this statement Pn is mathematical statement Pn is true for n is equal to 1. Basic. For n left hand side P1 is the 1 square
Place it and I put 1 upon k into 1 into 2 minus 1 plus 1 is 2 minus 1 is 1 is 2 for n is equal to 1. The statement, mathematical statement is true for n is equal to 1. Now I am going to assume that this mathematical statement is true for n is equal to k, where k is an arbitrary number. It is not. Okay, so let me replace n by k. So 3k will become 1 square plus 3 square plus 5 square plus so on 2k minus 1. These all formulas are important. You should remember this, that what is the sum of the squares of three odd numbers. That will be important later on also. It is very useful also. 1 square plus 3 square plus 5 square. This we have assumed to be true. Now we will prove, let us prove that here for n is true for n is equal to k plus 1. If I could prove it to be true for n is equal to k plus 1, then I'll be able to say that it is true for n is equal to 1, it is true for n is equal to k, and it is true for n is equal to k plus 1, and it is true for all that will be there. Now let's see what we do. Plus, will be replaced by what? K will be replaced by k plus 1. So 2k minus 1 will become 2 into k plus 1 minus 1. It will become 2k plus 2 minus 1. That is 2k plus 1. So it becomes 1, 2k plus 1. So when it will come out, when you open it out, it will become 2k plus 1. So this side, this complete thing will be correct. Not from k, 3k minus 1 and 2k plus 1. And this, when you will open it out, it will become 2k plus 1 plus 2k. You can take 3 LCM, or you can take out 1 upon 3, 2k plus 1 upon 3, 2k plus 1, 2k plus 1. 2k plus 1 is here, 2k plus 1 whole square is here, so I can take out 2k plus 1 from what will be left? It will be left 3 is 2k minus 1 and plus 2k plus 1. Now it is simple algebra, we have to solve it. Probably we'll get a trinomial and we'll solve the trinomial. We'll factor this out. 2k plus 1 is 2k squared minus k plus 2k plus 1. So it will become minus 1.3 2k plus 1 and 2k squared plus 2k. Now, can we factorize this 2k square plus k plus 1? Can we factorize 2k square plus k plus 1? Now we have made a mistake. So p to the 6. Here, it is k, right? Now you have to take out 3. What do we get here? We get 2k squared plus 5k plus 2. So 2 3s are 6. 2 3s are 6. So 1 upon 3 2k plus 1. 2k squared plus 2k plus 3k plus 2. And common 1 upon 2k plus 1. These mistakes are made here. That is why I prefer you take LCM first and then take out these. Because then you will don't take 3 here. So this is 1 upon 3 common, but this is not multiply here. So it is important that you take LCM and then you will take out common. You can make that. 3 plus 1. 3 plus 1. Now let us see what is common. 1 upon 3 plus 1. Let us see 2 plus 1. Now let us put whether it is equal to the given statement or not. Let us try it. Let us put n is equal to k plus 1. If I put n is equal to k plus 1 in this, then it should come the same. Then it is all right, otherwise not. So let us put here. Then n is made out of k plus 1. So I get 1 upon 3 k plus 1. 1 upon 3 here, I get k plus 1. Now, if I multiply, if I replace n if I put k plus 1, so it becomes 2k plus 2 minus 1, so it becomes 2k plus 1. And if I put n is equal to k plus 1, it will be 2k plus 2 plus 1, it will be 2k plus 2. So you get all the values, 2k plus 1, 2k plus 3, k plus 1, 1 upon 3. And so 3 is 2k into k plus 1, 2k plus 1, 2k plus 3. So it is true. Pn is true for n is equal to 0, n is equal to 1, n is equal to k, or n is equal to k plus 1. So it is true. So it is true. All the values greater than or equal to 1 and it is 1 or within verify. Yes. Now let us see question number 5, where it says the statement is 2 plus 2 squared plus 2 plus 2 to the power 4 plus 2 and 2 to the power n. That means we are having powers of 2, starting with 1, 2, 3, 4, 5, 8. And it says it is 2 n minus 1. We have to prove it using the mathematical induction, principle law of mathematical induction. So the first step again is to be true for n is equal to 1. Let us prove it to be true for n is equal to 1. N is equal to 1 means P1 left is 1. So the value is P1 2. If I take the right hand side, the value is P1 and then the 2 is 2 to the power 1 is 1. So left hand side is equal to right hand side. Now let us let us assume that we choose for n is let us choose for n into k. N into k means that n is very large. K, pk. It is important, this step is very important. I'm making in every question I'm talking to you that this step is very important, that we have to use it in the next step. And what is the next step? Let us use Q plus 1. In place of n, I'll write Q plus 1. So pk plus 1 total here 2 plus 2 square plus 2 plus 2k is equal to 2 to the power 2k minus 1 and plus and that is 2 to the power 2. So this is what 2 into 2 to the power 2 minus 2 plus 2 to the power 3. I broke it up. K plus 1 I wrote as 2 to the power k, 2. Now these two can be combined with the same. This is the same. This is 2 to the power. If you take 2 plus 2, 2 to the power 2 to the power, it will become 2 plus 2 is 4. So I get 2 to the 2. Now what? We can take out 2 points. If I take 1, or it will be 2 to the power 3 plus 1. This is 2 to the power. So both bases are same, powers will be added in the 2 to the power 3 plus 1. Now let us see whether it satisfies this condition. Yes, if you replace in place of n, we have to do k plus 1. So 2 into 2 to the power k plus 1 minus 1. So it is true. It is true, it satisfies this condition. It satisfies the given condition. So Pn is true for n to the 1 k. We are always going to prove it for 3 values. N is equal to 1 we prove, n is equal to k we assume, n is equal to k plus 1 we prove. So k means any value, k plus 1 will be the next number. So if it is true for any 2 arbitrary numbers, that means it is true for the value of x. So whatever the value is, true for all the values of n.
Now let's see the next question, question number 6, in which he has given the statement that 1 into 2 plus 2 into 3 plus 3 into 4. Notice that 1, 2, 3, then the next number 2, 3, 4 plus n into n plus 1 is equal to n into n plus 1 n plus 2 upon 3. I told you it is very important to remember these things also because they will help you later on. Sometime you get a series like that, you can directly put the value n into n plus 1, n plus 2 upon 3. Now we have to prove this statement using the principle of mathematical induction. Now what do? We prove it to be true for n is equal to 1. If n is 1, this is the basic step I am not writing. If n is equal to 1, then P1 left hand side P1 is 1. 1 into 2, that is 2, and right hand side will be V1. Instead of n, I'll write 1 into 2 into 3 upon 3. So 3 will cancel, 1 into 2 is 2. So true. Left hand side is equal to right hand side. So it is true, this mathematical statement is true for the value n is equal to 1. But it doesn't prove anything because it may be true for n is equal to 1. What about the remaining numbers? So for that we have told you that how do we do with the method of principle of mathematical induction, that we will assume that this statement is true. Assume Pn is true for n is equal to k. It is true for n is equal to k. So pk would be equal to 1 upon 1 plus 2, 2, 3, 3, 4, and k into k plus 1 is equal to k into k plus 1 into k plus 2 upon 3. Now this is an important statement because we will be using it in the next step. Now let us prove Pn to be true for n is equal to k plus 1. Let us prove that this is to be true for n is equal to k plus 1. That means we will replace n by k plus 1. So pk plus 1 will be 1 into 2 plus 2 into 3 plus 3 into 4 plus so on, k into k plus 1, and the next will be k plus 1 and k plus 2. Because k will be replaced by k plus 1, it will be replaced by k plus 1, it will become k plus 2. So we will be adding these steps. Now it is equal to what? It will be equal to k into k plus 1, k plus 2 upon 3, and then k plus 1, k plus 2. I would suggest take LCM because we forget sometime. So let us take the LCM. Let's take 3 as the LCM. It will become k plus 1, k plus 2, plus 3, k plus 1, k plus 2. Now you can see that k plus 1 and k plus 2 are common in numerator. K plus 1, k plus 2 is taken out common. What will be left? K plus 3 upon 3. So pk plus 1 is equal to this. Now let us see whether it is true or not. Let us replace n by k plus 1. If in place of n I put k plus 1, so k plus 1. If I put n is equal to k plus 1, it will become k plus 2. It is k plus 2. If I replace n by k plus 1, it will be k plus 1 plus 2. That will be k plus 3 upon 3. So it is true. Hence, Pn is true for n is equal to 1, n is equal to k, n is equal to k plus 1, true for all values of n. So it is true for all values of n. Every question we are going to use the same principle. First of all, we will try and say that the given mathematical statement will prove the given mathematical statement to be true for n is equal to 1. Then we will assume that it is true for n is equal to k, and then we will say it is true for n is equal to k plus 1. The next question we have is to prove that this mathematical statement is true. 3 into 2 to the power 2 plus 3 to the power 2, 2 to the power 3. They just notice the powers of 3 are increasing by 1 and the power of 2 are increasing by 1 also. But Already the difference of power is 1 here. 3 to the power 1, 2 to the power 2. That means the difference between the power of 3 and 2 in the term is 1. So 3 to the power n last term is equal to into 2 to the power n plus 1. The difference of the powers is 1. Is equal to 12 upon 5, 6 to the power n minus 1. Again, I would say it will be better if we remember these statements. It will be helpful somewhere later on. Let us take the basic step for n is equal to 1. Left hand side P1. This is Pn, so left hand side of this is this and right hand side is here. So 3 into 2 square against 12. 3 4s are 12. Right hand side Pn will be 12 upon 5 and 6 minus 1, that will cancel, so 12. So it is true. Left hand side is equal to right hand side. So this statement, given mathematical statement is true for n is equal to 1. Now let us assume that the statement is true for n is equal to k. Let Pn be true for n is equal to k. K is any value. Time and again I am saying k is any value of n. So pk will become 3 into 2 square plus 3 square 2 cube plus 3 to the power n. In place of n it is k, and 2 to the power k plus 1 will be equal to 12 upon 5, 6 to the power k minus 1. Now this assumption is going to be very important. We are going to use it in the next step. Let us prove Pn is true for n is equal to k plus 1. So let us replace n by k plus 1. So pk plus 1 will be 3 into 2 square plus 3 square 2 cube plus so on plus 3 to the power k 2 to the power k plus 1 plus 3 to the power k plus 1 and 2 to the power k plus 2. We have written next. K is replaced by k plus 1, so k plus 1 will become k plus 2. And this portion already I know. This portion we have assumed already. 3 into 2 square, 3 square, 2 cube, 3k, 2k plus 2 to the power k plus 1 is this. So let us put the value. Okay, let's put it here. 12 upon 5, 6 to the power k minus 1 plus 3 to the power k, 3 to the power 1, 2 to the power k, 2 to the power 2. I have broken up the powers. 3 to the power k plus 1 is written as 3 to the power k, 3 to the power 1. It is written as 2 to the power k, 2 to the power 2, so it is 4 3s are 12. 12 upon 5, 6 to the power k, minus 12 upon 5, okay, plus 12. 3 into 4 is 12, and 3 and 2. Because powers are same, bases can be multiplied. 6 to the power k. Okay, let's take 5 as LCM. Let's take 5 as LCM everywhere. Let's multiply it by 5 upon 5. So LCM will become 5. Let's take 5 as the LCM. So it will become what? 12, 6 to the power k minus 12 plus 5 into 12, 6 to the power k. Now in these two terms, 1 upon 5 you write separately. In this term and this term, 12 into 6 to the power k is common. 1 plus 5 will be there, minus 12. In these two terms I have taken 12, 6 to the power k common. So what will happen? 1 upon 5, it will become 12 into 6k plus 1. Why? 1 plus 5 will be 6, and 6 into 6k plus 1. 6 into 6k will become 6 to the power k minus 1, minus 12. I can take 12 forms. It will become 12 on 5, 6 to the power k plus 1, minus 1. Now this is exactly what the first is there. In place of n, I have put k plus 1. So it is true. So Pn is true for n is equal to 1, n is equal to k, and n is equal to k plus 1. So it is true. It is true for all n. Question number 8 I have to prove Pn is equal to 1 into 3 plus 3 into 5 plus 5 into 7 plus 2n minus 1 into 2n plus 1 is equal to n into 4n squared plus 6n minus 1 upon 3. Again the same method will be applied. Let n is equal to 1, so left hand side P1 will be 1 into 3, that is 3. Because the first step is 1 into 3, so it becomes 3. Right hand side P1 will be what? 1 into 4 plus 6 minus 1 upon 3. 10 minus 1 is 9, 9 upon 3 is 3. So left hand side is equal to, the right hand side is equal to 3. So it is true for n is equal to 1. This statement is true for n is equal to 1. Now I am going to try I will assume it is true. Let us assume it to be true for n is equal to k. I'll assume it is true for n is equal to k. I'm going to assume it is true for n is equal to k. So let us see what happens is that pk will be equal to 1 into 3 plus 3 into 5, so on, plus 2k minus 1, 2k plus 1 is equal to k into 4k squared plus 6k minus 1 upon 3. Now if it is true, then this will happen. We have assumed this is to be true. Then let us prove it to be true. Let us prove it to be true for n is equal to k plus 1. Let us assume, we have assumed it is true for n is equal to k. Now I am going to prove it to be true for n is equal to k plus 1. Let us see what happens. pk plus 1. p1, pk plus 1. That is the order. 1 is to 3 plus 3 is to 5 plus 2k minus 1, 2k plus 1, and now what are we doing? K is replaced by k plus 1, so it will become 2k plus 1 and 2k plus 3, because if you replace k by k plus 1, 2k plus 2 and minus 1, 2k plus 1, and if it is 2k plus 2 plus 1, it will be 2k plus 3. Now this is equal to this, k into 4k squared plus 6k minus 1 upon 3 plus 2k plus 1 2k plus 3. Let's take 3 LCM. K 4k squared plus 6k minus 1 plus 3 into 4k squared plus 3 to the 6k plus 2k plus 3 upon 3. Let's open all the brackets. Let's open all the brackets. It will become 4k cubed plus 6k squared minus k plus 12k squared plus 6 plus 2 8, 3 8s are 24k plus 3 3s are 9 upon 3. Now it will become 4k cubed plus 6 plus 12, 18k squared plus 23k plus 9 upon 3. 4k cubed plus 6k square, okay, 18k square plus 23k plus 9. Now here it is a little trick in this question. 18k square, I'll break it up as 4k square plus 14k square. I'll tell you why. I'll break it as 4k cubed as it is. 18k square will be 4k square. Why 4k square? I can take 4k square common. Plus 14k square. Now 23 I can break it up as 14 and 9. 14k plus 9k plus 9. Why? Again 14k square, 14k I can take 14k common. 9k and 9 I can take 9 common upon 3. This is just a little trick in this question, nothing else. So what we will do is, you take 4k square common, it will be left k plus 1. You will take 14k common, it will be left k plus 1 plus 9 common, k plus 1 upon 3. What will you get? You will get k plus 1 is common. In place of n, because we have replaced by k plus 1, I'll write it here. K plus 1 will come out common. And it will be what? 4k squared. 4k squared. 4k squared plus 14k plus 9 upon 3. If you put in place of n, k plus 1, in place of n, k plus 1, you will get the same thing. It is true. You can try it and you will find that it is true. So the statement is true for n is equal to 1, n is equal to k, and n is equal to k plus 1. Hence, this statement is true for all given values of n. These are enough questions for one video. I will be giving you more questions in the next video.